Okay, so this is the 2022 paper, so the first paper after the pandemic, the higher version. I've got a slightly bigger version for this video, and the picture I'm looking at is upside down, so you'll have to bear with me if things go a bit wrong. So it says here, polymer gels are commonly used in disposable nappies. A company that manufactures disposable nappies was investigating the effect of temperature on the mass of water the polymer gel in their nappies is able to absorb. The results collected using water at 40 degrees Celsius is given below. The initial mass of the polymer gel bead was 0.035 grams. So we can see from the results that initially we've got that 0.035 with no water added. Okay, the mass of water is 0, and then as we go down the table we can see that the mass of water increases quite drastically to start with. So the first question asks us, the percentage increase in the mass of the bead is calculated by using the following equation. So the percentage increase is the mass of water absorbed, okay, divided by the initial mass of bead times 1000. Calculate the percentage increase in the mass of the bead after 2 hours. Give your answer to the nearest whole number. Okay, so for the 2 hours, we can see that there, it's this row here. And what we need to do is take the information from the table and put it into the calculation. So mass of water absorbed, that's this column here, is 4. So the mass of water is 4.0 grams divided by the initial mass of the bead, which of course is 0.035. So 0.035 grams, and we're going to multiply that by 100 to get our percentage. So if we take our calculator, which obviously you wouldn't be able to have this calculator in your exam because this is a mobile phone, but for the purposes of this demonstration I think it'll do. 0.035 and then times that by 100. Okay, and that gives us 11428.57. okay, and if we round that up to the nearest whole number, that gives us 11429. okay, because we're rounding that up to a 9. Moving on, what properties polymer gels does the figure calculated in part 1 demonstrate? And it demonstrates that gels can absorb much more water than their mass. I'm sure I could have put that better, but much more water than their mass. Okay, so or many times as much water, or hundreds of times more water. Okay, so this is a percentage increase, so it's a big old percentage there. Okay, it's 11,000%. Okay, moving on now. On the grid below, plot the results using water at 40 degrees Celsius and draw a suitable line. Use the mass of water absorbed by the bead to 1 decimal place. The results using water at 10 degrees Celsius have been plotted. Okay, so we better plot this. So if we look at the results, so they'll be off screen for you, but I'll make sure that I can see them to try and save a little bit of time. Okay, so obviously at 0 we've got a 0 mass. After 2 hours, the water absorbed is 4 grams. Okay, so we've got 4 grams there. After 4 hours, it's 6 grams. After 6 hours, 7.28. So we're rounding that to 1 decimal place. That's 7.3. So here's 7, and then 7.3 will be there. 8 is 7.9. Okay, so there's 7.9. 10 hours, 8.18, which is, so 8.1 rather, so 8.1, which is here, and then after 12 hours, also 8.1. Okay, and we need to draw a suitable line, so we can use this line as sort of our inspiration, so we can pretty much draw a line that goes through the points in a nice smooth curve, levelling off at the top. Okay, so it says give differences between the absorbing properties of the beads using water at 10 and at 40. So we can notice, if we look at the graph, that the rate of absorption, okay, at 40 degrees Celsius is higher because the line is steeper, and also the maximum amount of water absorbed at 40 degrees Celsius is higher, okay, because it's 8 grams rather than the just over 5 grams for the beads at 10 degrees Celsius. So the rate of absorption at 40 degrees Celsius is higher than at 10 degrees Celsius, and the maximum mass of water absorbed at 40 degrees Celsius is higher than at 10 degrees Celsius. Okay, so we move on. Okay, so this next question is taken from the acids and alkalis section of your syllabus, and it's a classic sort of question, a reaction scheme, but we're given a bit of extra information here. So the reactions of acids with metals, bases and carbonites are summarised in the following equations. So we need to be mindful of the products. Okay, so we've got hydrogen when it's just a metal, water when it's a base could be a metal oxide or a metal hydroxide, and then it's salt, water and carbon dioxide when you've got a carbonate. So with that information in mind, we can have a look at the reaction scheme below, and the reaction scheme questions all start off in the middle, or 99% of the time, and from the middle we've got a variety of different reactions that could happen. So for example, hydrochloric acid reacts with KOH, so KOH is potassium hydroxide, and that would be a base. Okay, it's actually an alkali, but it's a soluble base. So that would be comparable with this equation at the top of the page. So we're going to get salt and water. So from that we can work out that substance D must be water, okay, because KCl, potassium chloride, is a salt, so substance D must be water because of this equation here and the fact that KOH is a base, or an alkali, a soluble base. Moving round, we've got hydrochloric acid reacting with substance A to make magnesium chloride, which is a salt because they all make salts, and hydrogen. So if you have a look at the top here, the only one of these three that creates hydrogen is this one, and consequently substance A must be a metal, okay, because we're making hydrogen, and if the salt is magnesium chloride, then that metal must be magnesium. So we can identify that as magnesium. Moving round again, we've got hydrochloric acid reacting with zinc carbonate, and so that would fall into a reaction described here, okay, because we've got the acid reacting with a carbonate, so there's the acid, there's the carbonate. We've got salt, which would be zinc chloride, water, which is identified here, and substance B, which must be carbon dioxide. Okay, so substance B is carbon dioxide. And then just to finish the job off, we move around again, we've got copper oxide, which again is a base. This time it's an insoluble base, so it's just a base, reacting with the acid. So acid plus base makes salt and water. So if we've got water being produced, then substance C must be the salt, and the salt produced when the copper compound reacts with hydrochloric acid is copper chloride. So that must be copper chloride, because hydrochloric acid always makes a chloride, and the copper provides the first part of the name. So I suspect we've done most of the questions by doing that, but let's have a look. So give the name of substances A and B. So we identified substance A as magnesium. Substance B we identified as carbon dioxide. and then a little bit sneaky if you like, the formula for substances C and D. So we've identified substance C as copper chloride. So what we need to do is quickly look at the table of ions to confirm our formula. So copper chloride, so copper is here, okay, Cu2+, and chloride is over here, Cl-, and if we do the seesaw method, we can see that 2+ is 2 minuses, so we need 2 of these, and that will give us the formula CuCl2. So if we go back and fill that one in, so there is CuCl2, and then substance D is hiding from me. Here it is, water. Okay, and I think we should be okay writing the formula of water as H2O. Okay, so that's completed those questions. Moving on now to part B. Complete the equation for the reaction between hydrochloric acid and sodium carbonate by writing a formula for sodium carbonate on the dotted line and putting a number in the box to balance the equation. So again, we can quickly refer to our table of ions for sodium carbonate. Okay, so sodium is here, Na+, and carbonate is over here, CO3 2-, so 3O3 2-. So if we put that on the here, we can see that this is a 2- charge. We'll need 2 of these to balance that, and that will lead us to a formula of Na2CO3. Okay, so we'll go back to the question. We can put in our Na2CO3, and then if we have a look over here, we can see that the 2 sodiums that are present there need 2 chlorines in order to make 2 lots of sodium chloride. So that would lead us to believe that we might need a 2 over here. And just to double check, that 2 HCl means we've got 2 hydrogens which reappear in the water as H2O, and then the carbon reappears in the carbon dioxide, and O3, well, 2 of the oxygens appear in carbon dioxide and the other one appears in the water, so that's all balanced. Now this next question says silver nitrate solution is used to identify the chloride ions present in hydrochloric acid. Give the observation made when silver nitrate solution is added to hydrochloric acid. So when you add silver nitrate to a chloride ion, you get a white precipitate of silver chloride. Okay, so white precipitate of silver chloride. So that's the observation, and then down here we need to tick the appropriate box to tell us what's happening. So the ions involved in silver nitrate and in hydrochloric acid are all aqueous. So with that in mind, we can go through and we can cross off any that involve solid ions. So it's not that one. And what's the other one? Okay, we also need to bear in mind that silver ions are positive because they are a metal ion. You can just double check that if you wish on the table of ions at the back. So silver should be here, they are, Ag+. Okay, so it's not going to be that one or that one. Okay, which leaves us with these last 2 here. Now silver chloride is a precipitate, which tells us it's a solid. Okay, so it's not that one, which leaves us with this one here. Okay, so Ag+, aqueous, and Cl- aqueous makes AgCl, which is a solid. Okay, so that's the correct answer to that part of question 2. Right, moving along. Number 3. Okay, so this is from the bonding and structure section of our syllabus. The diagram shows the transfer of electrons taking place during the formation of sodium oxide. So we can recognise here that we've got a metal, sodium, and we've got a non-metal, which tells us that this has got to be ionic bonding. So metal and non-metal is the indicator of ionic bonding. So which we've just Next question is, what type of bonding is it? Okay, so it's ionic bonding because you've got a metal and a non-metal. It's also ionic bonding because you've got the full transfer of electrons rather than the sharing of electrons. So state what must be done to sodium oxide so that it will conduct electricity. So once sodium oxide forms, it becomes an ionic lattice, which contains charged particles. However, they can't move. So in order to make sodium oxide conduct electricity, we need to melt the sodium oxide. So the Na sodium oxide needs to be melted to allow the movement of the charged ions. So in order to conduct electricity, a material must have charged particles which can move. So it does have charged particles as a solid, but they can't move, so you have to melt it in order for them, in order for the material to conduct electricity. Okay, moving on to this next question. So we'll draw a dot and cross diagram to show the bonding in a molecule of tetrafluoromethane. At first glance might seem a little bit daunting. However, if we just break this down, carbon and fluorine are both non-metals. You can confirm that on the periodic table, and consequently this must be covalent. So we must need to show the sharing of electrons. Okay, so if we have a look at this, carbon 2,4 is going to need 4 extra electrons. Fluorine 2,7 only needs 1 extra electron. So if we draw our carbon in the middle, it's going to be similar in many ways to a methane. Okay, and if we draw our 4 electrons from the carbon there first, so that's the outer shell of carbon. We only need to draw the outer shell for these diagrams, otherwise they get complex. And then around each of these electrons we're going to draw a fluorine atom. Okay, so we need to make sure that there's an overlap that includes the atom from the carbon. That one's a bit of a shaped fluorine, but there we go. And put F in the middle of each of these to ensure that we know that these are fluorine. And according to the version here, there's 7 electrons of fluorines. Now one has to go in the overlap. That shows a pair of electrons, which is what we mean by covalent bond. And that's 1 electron of fluorine to draw in 6. So you've got the total 7 in the section at the top of the question. If we just finish that, we've done the right. So the carbon share of 8 electrons, if you can, and fluorine has electrons, 3, 4, 6, 7, and they're all. So then come the next question. Tetrafluoromethane, covalent gas at room temperature, has a low point. The bonds here and here, these are but that are intra bonds. The bonds this particle tetrafluoromethane very weak. That's why the very low. So we can see molecular goes between force O is so we've made 2 questions. One is easy. Bond to break. Attraction, which only so tetrafluoride easily. So part of the question it's got extreme different properties. Oxides mean of silver dioxide. Scale titanium commonly used self-clean. Give the reason effective. So in some, it's complex. Okay, so titanium dioxide reflect you it to be a good self-cleaning catalyze between the and the dirty, so they reaction that remove window. Okay. When free oxide takes place, it reacts with an aluminium. This is the iron, and that becomes this reaction, the thermite reaction to repair. You can see, so you've given out the iron liquid. You can't really down between, and it welds the two smooth reaction, and this is more reaction. Okay, and balance. We can use the word equation as iron and 3. So it follows the same path as the iron oxide here. And we just need to double check that we balance it. So we've got 2 on this side, we've got 1 on that side, so we need to put a 2. Okay, and then the Al2O3, Als, 2 Als, O3. So that's then question section in iron oxide. If we look at the what we need is, first of all, work MR present, and there's atoms present here. Devolve the mass of iron dioxide. The actual figure is in. These are all in grams. We're looking for mass increase. And iron 3 oxide is the 56 plus the 48. Each oxide weighs 16, of them weighs and 48. Right. Again, 112, okay, because we've got the mass of iron, the mass of 12 plus 460 as so calculation 1 can't see that 70% iron. Okay. Part B of this question. Carried out a series of displacement reactions in dropping to a solution of nitrate of a different tone. Okay, so you might recognise it's got iron, can't read, copper, tin, nitrate. So, it was not necessary to carry out place crosses on the diagram to show which test is carried out. Zinc nitrate, the reactivity of zinc in nitrate. The same is tin and not from nitrate is true. No difference in the equation shows the reaction between iron and copper 2 nitrate solution. So we've got 2 Fe's reacting with 3 coppers. Maximum when 0.224 grams of iron is. We can see that for every 3 moles, so for 2 moles of iron, we're told the mass of iron used, and we're given the AR of iron. So with 2 values, we can work out a number of moles. Okay, the AR actually in 56. 2 grams per on the screen. 0.56 gives us 0.004 moles. Now, for every 3 moles of copper, bigger than that value. So therefore 1.5 equals 0.006 moles of copper. Well, this is the number of moles. The question asks for the maximum mass. So if we multiply that value by 5, point gram on the calculator. Five to 0, 5, and that gives us 0.38. Not only is that all this value, okay, so 0.3. And then let's just double check we haven't quote it. We're all right. The fourth what's going on here. The zinc compound. So in order to electrode picture will be positive, it will be negative. That's the reaction. So node is a positive electrode. So let's balance the equation on that side of the equation. Each of these chlorides will give away an electron, okay, to there. Balance the equation. So it asks us to explain oxidation using this. So if we remember that remember that when we're talking about oxidation, so this minus ion. An electron ion lose their electrons to become a chlorine molecule. So molecule. Mass reduced on the cathode. Zinc is deposited because the zinc ions arrive. They're given electrons, they become zinc atoms, and they're stuck onto the electrode. So first of all, record the mass electrolyte. You put it on a balance, and you work out its mass. Remove the cathode. It says using this method So what can happen is that the picks up not just the zinc, but also it picks up electrolytes, so the zinc chloride embedded in the zinc metal as you pull it out of the dish. Okay, so increasing just electrolyte by mistake. So yes, why this method cannot be used to measure the mass of in this process. So what we need to remember here is that it's a gas. Okay, it doesn't say in the equation. We could put a little g there, and so basically it's given off and be collected easily. In technical terms, chlorine. No. The bar charts. I'll put them on the screen. Here we go. The relative sign demand of some fractions obtained from the demand for the smaller fractions is and for stable we can, so in other words longer um, chain length molecules have great demand, low relationship. Important. That word there is used to overcome the problem of insufficient supply of sums fractions. State what is meant by cracking given the conditions needed for the process. So cracking is breaking of chain. Temperature. It's done in the lab. The catalyst in the lab can be crystal. Okay. Mention that it can be high temperature and industrial process. We can try another. On the page. So vaccine Okay, so part B says C4H10 has two isomers. Give the meaning of the term isomers. So isomers are different structures of the same chemical formula. Okay, and it asks us here to draw the structures of both isomers of C4H10. Okay, so the first isomer we can draw would be a simple carbon chain. So 1, 2, 3, 4, and then each carbon has to have 4 bonds, and we can tell from the formula here that this fits the general formula CnH2n plus 2, which is the general formula for alkanes. So we've got 4 carbons, so 2 times 4 is 8, plus 2 is 10. So this is an alkane, so every carbon now has to have 4 bonds. Okay, so each carbon, if you look, has got 4 bonds, and attached to each of those is a hydrogen. And just to double check that we've matched our formula with our structure, we know we've got 4 carbons, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Now if we take this structure and just take off one of the carbons of either end and draw a 3 carbon chain, and then add that carbon we've removed up here, or it could go down there, it makes no difference, and then add in the bonds necessary to ensure that each carbon has got 4 bonds, we will then end up with this new isomer. So it's the same number of atoms but a different structure, and oh, there's one missing there, that will be a different isomer. Okay, and the question doesn't ask for the name, but in the case that it does in a future exam, this is simply butane, because it's got 4 carbons and but is the prefix for 4 carbons. This one is methyl propane, and that's because the longest chain we can see in any way we count it is 3 carbons, so there's 3 carbons there, 3 carbons here, 3 carbons here, so that's the prop bit. There's no double bond, so it's ane, and then the methyl tells us about a side chain, so again it could be either that one or that one, depending on which carbon chain you take as the longest. So that's methyl propane. Okay, this next question, an awful lot of reading to do, okay, which is usually good news because it usually means that all the questions are based on comprehension rather than any prior knowledge. So as long as you take the time to read it in the exam, you should be able to score quite highly. So it's well known that plastic bags are a major source of litter. These bags can exist for a very long time, ranging from tens of years in the natural environment up to 1,000 years in landfill. The use of plastic bags is now banned in some countries. These countries commonly use bags made from paper or cotton, which do not cause the same litter problem as plastic bags. Paper or plastic. Most people assume that a paper bag is better for the environment. However, because paper bags are almost 10 times heavier than plastic bags, they produce a greater mass of waste. On the other hand, paper bags are biodegradable. They do not lead to the same problem with litter as plastic bags. When deciding on whether paper is more suitable than plastic for making shopping bags, information from the life cycle assessments or LCAs of both materials must be taken into consideration. Some of the findings from LCAs of paper and plastic bags are shown below. So, plastic bags are toxic to aquatic environments, and their production is more likely to deplete natural resources. Plastic bags use 70% less energy in their production compared to paper bags. The processes used in paper production cause atmospheric acidification and eutrophication. So atmospheric acidification causes acid rain, and eutrophication is where the water courses, rivers and streams and lakes to some extent, produce too much green life and they become stagnant as a result. The production of 1 million paper bags produces 51 tonnes of carbon dioxide compared to 31 tonnes for plastic bags. 693 kilojoules of energy is needed to recycle 1 kilogram of paper compared to 8 kilograms for the same mass of plastic. and then 4,546 litres of water are used to produce 1,000 paper bags, compared to 177 litres for the same number of plastic bags. Paper bags are made from trees, and plastic bags are made from ethene, okay, which is derived from crude oil and by cracking. Paper bags are 10 times heavier than plastic bags and therefore have more associated costs. So on reading these findings, it's important to consider all factors relating to sustainability when deciding on the most suitable material to make shopping bags. We should not just be thinking about what happens to them when we throw them away. Okay, so the questions. Use the information in the passage to compare the mass of waste and volume of litter generated from the use of plastic bags. Okay, so we need to make sure we quote the information that's available to us so that we're answering this question fully. Okay, so paper bags produce a greater mass of waste, okay, so it's heavier than plastic. Okay, so conversely the plastic bags produce a lower mass, okay, so that's one point you can make there. Paper bags cause more litter, okay, due to this reason. So, sorry, plastic bags cause more litter, sorry. Plastic bags cause more litter. Plastic bags cause more litter. And then conversely you could talk about paper bags producing less. Okay, so we've got those are the two marks, to be honest. So greater mass for the paper, but plastic causes more litter because they're not biodegradable and because they're lighter, so they can blow around more easily. Okay, use the information from the LCAs to tick whether each of the factors supports or opposes the use of paper bags in preference to plastic bags. So, impact of waste on marine life. Okay, so that supports the use of paper bags. Water consumption in production. Now, there's more water used to make paper bags than plastic bags, so that opposes the use of paper bags. Energy used in production. Well, there's more energy used to produce the paper bags than the plastic bags. Carbon footprint generated in production. So if we look at the fact about carbon dioxide, that's an indicator of carbon footprint. So once again, paper bags are less environmentally friendly than plastic bags. Energy used in recycling. Okay, so if we take out the 693 compared to the 8 kilojoules, so that's again against paper bags. Cost of transporting waste, again, poor paper bags lose out. Okay, so we've got there 6 points, so you'd have to get all 6 to get the 3 marks, and then it would be a sliding scale down to 0. Right, the use of which type of bag is more likely to be linked to the erosion of limestone buildings? Give a reason for your answer. Now, limestone buildings are affected badly by acid rain, okay, because limestone is calcium carbonate, and it reacts and basically dissolves the limestone. So we need to find out which causes the most acid rain, and if we read from the information, the process used in paper bag production causes atmospheric acidification. Okay, so I think again paper bags lose out. Okay, so paper bag and the method of production causes atmospheric acidification. In other words, the atmosphere absorbs acidic compounds which then form acid rain that falls on the statues. Okay, so we've got to turn to the final question now. So this graph here actually describes a type of titration reaction. Okay, not the one that you'll have done as part of your practical, but it's still the same idea. So the graph shows how the temperature changes when dilute hydrochloric acid is added gradually to sodium hydroxide solution. Okay, you can't see that there. So at the bottom of the graph, we can see that the volume of acid is increasing. On the side, we can see that the temperature scale. So initially, the temperature increases rapidly, showing that there's a chemical reaction going on. So this is acid reacting with oxide. So this will be a neutralization reaction. As we add more, the temperature continues to rise. As the reactants start to run out, okay, or as the sodium oxide starts to run out, because we keep fresh hydrochloric acid, the rate to rise slows down until we get maximum value. So this value top here, tests the reaction is now over the sodium hydroxide reacted. So any fraction of is similar the acid to mix reactive, and again the mix cools. So we're just adding and it's down. So right here. And let's have a look at the pH of also changed hydrochloric added to the graph, and the pH high because sodium hydroxide, and as we reduce, and the likelihood if you reach here be around because the point at which it is neutral, and because more and more the pH was because the solution could become, because you're adding and there's no react. Explain shown in pH, you do equations. Okay, we need to mention as is added rises to neutralization. Place temperature reduce acid Q. So H don't know exactly alkaline pH 7 a mixture is added there is no side so this is of the mixture now decreases due to this. Okay, so for that question, hydrochloric reduces chloride and water. Give the water is formed during the reaction. Okay, so hydroxide is sodium ions and chloric acid.